Hello and welcome back to our course Data Analysis in Astronomy and Physics, Lecture 9, Error Analysis. Today we will talk about error analysis and error propagation, quantify a term named covariance, and will also look back at probability distributions and how to combine distributional properties when we want to quantify the variance of a quantity with more details, in contrast to what is possible with simple measures such as a variance or a standard variation. Volume of a box with length L, width W and height H. So we measure each of the three dimensions to be L0, W0 and H0, and we combine these measurements to compute the value for the volume V0. How do the uncertainties in our measurements L0, W0 and H0 affect the resulting uncertainties in the final volume? If we knew the actual errors, delta L, so the difference between the true value L and our estimate, and so forth, in each dimension, we could obtain an estimate of the error in the final result of the volume by expanding the true volume about the point L0, W0 and H0 in a Taylor series. The first term in the Taylor expansion gives the volume is approximately V0 plus delta L times the partial derivative of the volume with respect to L plus delta H times the partial derivative of the volume with respect to H plus delta W times the partial derivative of the volume with respect to W, from which we can find delta V being the difference of V minus V0. So these are the partial derivatives of the volume with respect to each of the dimensions evaluated at the point L0, W0, H0. They are, so to speak, the proportionality constants between changes in the volume and infinitesimally small changes in the corresponding dimensions. The partial derivative of V with respect to L, for example, is computed with the other variables W and H held fixed at the measured values, as indicated by the subscript. This neglects higher order terms in the Taylor series. For very large errors, we would need to include them. For our example above, we find an error of delta V is approximately delta L times W0 times H0 plus delta H L0 W0 plus delta W L0 H0, which we could evaluate if we knew the uncertainties in our measurements of the dimensions. In general, we do not know the actual errors in the determination of the dependent variables. Instead, we may be able to estimate the error in each measured quantity, or to estimate some characteristics such as the standard deviation sigma or the probability distribution of the measured quantities. Now, how can we combine the standard deviation of the individual measurements to estimate the uncertainty in the result? Suppose we want to determine a quantity x, which is a function of at least two measured variables u and v. And we want to determine the characteristics of x from those of u and v and from the fundamental dependence x, which is a function of u and v. We assume that x bar the mean value is the function of u bar and v bar. The uncertainty in the resulting values for x can be found by considering the spread of the values of xi resulting from combining the individual measurements ui, vi into individual results. So for computing x from a sample of measured u and v values. And in the limit of an infinite number of measurements, the mean of the distribution will approach the population mean, x bar, and we find the variance of x is the limit for very large n's of 1 over n times the sum over all the squared deviations of xi minus x bar. And similar to the example, we can now express the deviations of our measured x minus the mean value in terms of the deviations of the ui, the u and the v values of the observed parameters. So the deviation of xi minus x bar equals ui minus u bar times the derivative of x with respect to u plus vi minus v bar, the derivative of x with respect to v, and so on for all the other parameters. And here this is a mistake. This should be left out. Now combining these equations, we get this one here, and we can now multiply out the square, and by collecting the first terms, we get the first term squared plus the second term squared plus the mixed terms, so this times this, plus all the other terms for additional parameters. So the first two terms here can be expressed in terms of variances of u and of v, because the sum over this term divided by n is the variance of u, and the variance and this term summed up divided by n is the variance of v, as also written down here in these two equations. And the third, so where are we? And the third term now is, in contrast to these terms here, a mix between deviation of u times deviation of v at the eth data point times the product of the two partial derivatives, and this term is called covariance of u and v, which is the sum of the product of the individual deviations. Here it's important to note that in contrast to the variance, which cannot be negative, this of course can return a negative number, because either of the two terms in the product can be a negative number.